Greetings everyone. I, Kalingiri Vinila and team Vision X is here to present AI-powered traffic queue analysis and violation detection. Today, I want to talk about the problem that we experience almost every day, that is urban traffic management. In cities, traffic congestion has become a serious issue, especially at major intersections. We often see long queues, unnecessary waiting at signals, and frequently rule violations like signal jumping and rash driving, etc. Even though traffic people are doing their best, the current system still have many limitations. Most traffic signals works on fixed time intervals, which means they do not consider real-time traffic density. At the same time, traffic police have to manually monitor the roads, stand for long hours, and continuously watch vehicles to identify violations. This requires a lot of time, energy, and efforts. And during peak hours, it becomes very difficult to analyze accurately. Another important issue is that most cities already have CCTV cameras installed, but these cameras are mainly used for recording footage only. Huge amount of data are collected every day, but they are not analyzed in real time, which means valuable information remains unused. Here, our solution comes in. We propose an AI-powered traffic queue analysis and violation detection system that transforms raw CCTV footage into real-time traffic intelligence. Our solution follows a clear and simple processing pipeline. First, we take a video input from CCTV cameras or recorded footage. Then we perform vehicle detection using deep learning modules like Vivo Ergo, which helps us identify different types of vehicles on the road. After that, vehicles are tracked to understand their movement patterns. Using this information, we perform traffic analytics such as estimating queue length and identifying congestions. Finally, all the results are shown on the dashboard, which makes monitoring easy and quick for traffic authorities. The key advantage of our system is that it works with existing CCTV infrastructure. So, there is no need for expensive hardware upgrade. It reduces manual efforts, improves efficiency, and helps traffic policies focus on only on critical situations. For this hackathon, we have developed an MVP that demonstrates the analytic and dashboard of the system. In future, this solution can be extended to adaptive traffic signals, automated violation reporting, and smart city application. Overall, our goal is to unlock the intelligence hidden in traffic data and make traffic management smarter using AI.
Now, vehicle detection and tracking. This is the core of our system. We use YOLO V8, a real-time computer vision model, to detect different types of vehicles such as cars, bikes, buses, and trucks. From live CCTV footage, we get the data and we assign a unique ID to each and every vehicle to track it continuously so that we can avoid double counting, and also allows us to understand how each vehicle moves through the road. Because the tracking is persistent, we can later use this data for speed estimation, behavior analysis, traffic flow measurements. This is the foundation of our entire traffic analysis system. Now, queue analysis. Queue analysis helps us to understand traffic congestions more intelligently. Instead of just counting the vehicles, we analyze queue length and queue density near the traffic signals. Queue length is how many vehicles are waiting during the red signals, while queue density shows how much road is occupied by the vehicles. This is very important because different vehicles occupy different spaces. For example, 2 trucks occupies more space than 5 bikes. By using this density instead of just vehicle count, our system provides a more accurate picture of traffic load. This data can be directly used for adaptive traffic signal control, helping signals adjust timing based on real-time congestion. Now coming to the violation detection. It focuses on road safety and rule enforcement. Our system detects red light violations by defining a virtual line. If a vehicle crosses this line while the signal is red, the violation is automatically detected. We also identify rash driving behavior such as sudden acceleration zigzag movement, or unsafe overtakes. For every violation, the system records a timestamp, vehicle image, and relevant evidence. This makes the system suitable not only for monitoring but also for automated and unbiased enforcement. Our solution can work with the existing CCTV infrastructure, making it practical for real world deployment.
The project, we used a combination of computer vision, deep learning, and visualization technologies to build an end-to-end traffic analysis system. Each technology here was chosen for a specific reason, like Python is used as the core programming language to integrate all modules smoothly. OpenCV, a computer vision library, handles video processing by breaking traffic footage into frames and drawing visual annotations like bounding boxes and stop line regions. For vehicle detection, we use YOLO, a deep learning object detection model that identifies different vehicle types such as cars, bikes, buses, and trucks in each frame with a high speed and accuracy. Once vehicles are detected, deep sort or a byte track is used for a multi-object tracking, which assigns a unique ID to each vehicle and maintains its identity across frames. This is essential for queue estimation and violation detection. Next, NumPy supports for numerical computations required for motion analysis and density calculations. Finally, a Streamlit web dashboard framework is used to visualize the results by displaying traffic metrics and annotated outputs on a simple web-based dashboard, making the system easy even to understand for a non-technical user. The next slide explains the main components of our system and how they work together. The first component is the video analysis module, where traffic videos are processed to detect and track vehicles and analyze the movement patterns. Based on these analysis, the system calculates important traffic metrics such as queue length, the total number of vehicles waiting before the stop line at a traffic signal, and queue density is the concentration of the vehicles within the queue area near the stop line. The violation detection component then identifies the traffic rule violations such as red light jumping and rash driving using trajectory based logic. All these results are passed to a visualization layer which includes annotated video output showing vehicles IDs, queue regions, and violation makers. In addition, a Streamlit dashboard presents summarized insights such as vehicle count, congestion level, and total violations. Together, these components convert raw traffic footage into clear, actionable traffic intelligence.
Now, let us look at the future enhancements planned for this project. In phase 1, we aim to implement multi-lane queue estimation. This helps the system accurately count vehicles across multiple lanes, including lane splitting and mixed vehicle types, which are very common in Indian traffic. In phase 2, we plan to add accident detection. The system will identify abnormal situations such as stationary vehicles in moving lanes or sudden collision patterns and generate instant alerts for emergency response. In phase 3, speed violation detection will be introduced using camera calibration and homography techniques. The system can estimate vehicle speed without relying on radar guns. Finally, in phase 4, we propose a smart signal advisory based on real time traffic density and queue length. The system can suggest optimal green light timings to reduce congestion and improve overall traffic flow. These enhancements will help scale the project into a complete intelligent traffic management solution. To conclude, this project demonstrates how traditional CCTV cameras can be transformed into intelligent traffic analysts using computer vision and artificial intelligence. The system provides explainable analytics where traffic conditions and violations are detected using transparent logic and visual evidence instead of black box decisions. It follows a modular architecture allowing independent development of detection, tracking, and analytics modules, making the system scalable and easy to maintain. The solution is designed for real world urban traffic capable of handling congestion, diverse vehicle types, and chaotic road conditions. Additionally, by using open source technologies like YOLO and OpenCV, the system remains cost effective and deployment ready. Overall, these projects converts passive traffic monitoring into an active, intelligent traffic analysis system and lays a strong foundation for future smart applications. Thank you.